Okay, so let's start with the presentation. So thank you for joining me for the presentation on how to perform the RF functional tests on STM32WL. So why should we even talk about this topic? You may find yourself looking for the microcontroller for your application, or you are already working on a solution with STM32WL. And then you are wondering if your PCB is working the way it is intended to. So usually you start with the hello world of embedded applications, and that is the LED blinking. And after that, since STM32WL is not only a microcontroller, but it has a radio peripheral on the same die. So you want to know if the radio part is also working. To do that, we have a set of functional tests inside the Cube WL package within the STM32 ecosystem. Our ecosystem provides the firmware package with a set of examples for each peripheral, tools to program and debug the microcontroller, and the part of the ecosystem is the set of functional tests for the radio. And following one of the software examples or firmware examples for the WL, the Lorawan AT slave, acting as Lorawan modem, it is possible to use subset of relevant AT commands for RF testing. So if you are not familiar with Lorawan, or you are already familiar, so just to remind you quickly, what is the Lorawan Networks and where is the link we should test if we have a PCB with STM32WL. So from the top, if I click it here, from the top we have the application server, which is responsible for your application. So for example, you are gathering some data, sensor data, so for example, a temperature, and you want to plot it into a graph and see the results over several months. But to get the data from your end device, you need something in between, and that is the network server, which provides the infrastructure and communication with the end device. And the network server communicates with the gateway, which is basically a very simple device, only transforming LoRa packets into TCP/IP packets. And basically, this whole area communicates over the internet over TCP/IP. And this is the link where we want to test our device, because we need to reliably communicate with the device over even a couple of kilometers, even though speaking about absolute range with radio devices, it is better to use the link budget. So what is the link budget? Link budget is a simple equation where we mostly control only one variable, and the other variables can be considered constant. So if we look deeply into the equation, it's a power output which is regulated, for example, in Europe by the EU, or in the respective country of operation, they have their own regulations. So for example, in Europe, it's 14 dBm maximum output, so we cannot move with this. Then there is the gain of the antenna. That is a design choice. And again, we can only go with the technology so far and have on a certain PCB a static gain. So we cannot move with this variable either. The last one is the sensitivity, and that is the only variable that can be moved in this equation. So to increase the link budget, we need to increase the sensitivity. Now, what is the sensitivity? Again, it's another equation. In the end, it's only with one variable. We have the signal to noise ratio and noise figure. So for a particular operation between two nodes without changing the position, without changing the environment, we have basically static signal to noise ratio and noise figure. Then there is the noise power density at 25 degrees Celsius. And the last parameter is the logarithmic function of data rate. And data rate is the only variable in this equation. So to sum this up, we can only change the data rate. So to increase the sensitivity, we need to decrease the data rate. And decreasing the data rate then means increasing the link budget. If we go back to the STM32 ecosystem, the most important part is the STM32WL. It's the package that provides drivers and middlewares with a set of examples to ease the development of your software or firmware on the STM32. From the Lorawan perspective, there are three most important examples. That is the ping pong, which is not strictly speaking Lorawan. Then there is the EndNode and AT-slave applications, which are backed by the Lorawan middleware in our libraries. Then there is the sub-gigahertz middleware. And for the stack and the whole application to run, we have the utilities like the timer server, sequencer, low power manager, etc. And on the bottom, we have the hardware abstraction layer. So that's the lowest part that communicates directly with the hardware. And in between, there could be also the board support package, which is responsible for helping you with our hardware evolution tools. So for example, for the STM32WL Nucleo. Now, because we will practice a little bit the functional test, what will we need to make one? So first of all, there is the STM32WL Nucleo, which its main feature is of course the STM32WL chip, and since it includes also a radio PHY, we need an antenna. So there is an SMA connector to connect an antenna. Then there is the ST-Link, which is a debugger to load firmware into the WL, and also it acts as a virtual COM port. So you can simply hook the UART from the WL through the ST-Link and connect by USB to your PC, and the UART will act as a virtual COM port in your PC. Then with the AT-slave loaded, you can either use the COM port terminal. So for example, Termite, Teraterm, whatever you are using or you are used to. And you will see a simple command interface. You send an AT commands, the AT-slave response. Or you can use the STM32 Cube Monitor, which is a graphical interface, basically a graphical wrapper around the AT-slave. And there is a dedicated flow for the AT-slave. STM32 Cube Monitor is basically a generic tool that can visualize and monitor data. It has a graphical flow based editor, so it's like not a programming strictly speaking, but connecting some blocks. It's based on the famous Node-RED application. It's basically a server then, and it runs on multi-platform, so it can run on Windows, Linux, or even Mac. Now to get to the AT-slave, first of all, you want to find the application, so we need the STM32 Cube WL package. that can be downloaded from st.com, or if you have or the STM32 Cube IDE or CubeMX, it will be located in the repository that is in the user folder. Within this package, then we had two projects where you find all the examples for each evaluation hardware board. So in the case of WL, so far only the Nucleo WL. Then you had two applications. You have also examples and other features. Examples are very simple. Examples are called the folder, and within these folders, it's very simple applications to toggle LED to communicate over I2C, and applications contains usually some middleware. So in our case, it's the Lorawan, and for use case of the Lorawan stack, we have the Lorawan AT slave located there. So first of all, we need to open the project in one of the famous IDEs. We can use IR, we can use Kyle, or we can use STM32 Cube IDE, which is a IDE developed by ST. It's free of charge, so you can just download it, open the project, compile the project, and load it into the microcontroller. You will also find STM32 Cube Monitor folder here, and that is important for the functional test because it contains the JSON file, which can be imported into the Cube Monitor. Now back to the AT slave. There are a couple of commands for the functional test and RF tests in general. So first of all, we can send simple AT command that will respond with OK. And then question mark will list all the commands. So we chose some of the commands here to describe them more. So we have the AT plus T-tone, or first of all, we need to AT plus T-conf to configure the radio the way we want it, meaning we want to transmit on a certain frequency, we want a certain spreading factor, power, etc. And then we can perform AT plus T-tone or RSSI tests. So basically T-tone is a simple unmodulated wave transmitted on the board, and its counterpart is the RSSI tone test, meaning it listens to the wave and measures RSSI. These two commands are also important for the certification because, or also during the development, you want to know how your RF matching performs on the PCB. So this is the test that is usually used in the RF lab. I would also mention in this case our RF lab in Prague, because not only you need to battle it yourself, we can also help you. And we have nice RF lab in Prague, but for that, it is really important to leave at least one UART, meaning both RX and TX on your PCB, at least as a test point, so that the AT slave can be loaded during the development, and you or my colleagues from the RF lab can perform the tests. Then we have AT plus TTX and TRX, which is only a functional test. So one of the boards is transmitting, the other one is receiving, and the packet error rate is calculated. For the Lorawan standpoint, we have the AT plus certif. So basically, it activates the state machine inside the stack to trigger certification mode, and Lorawan certification can be done, and eventually, based on this test, you receive your LoRa Alliance certification. And then any test can be stopped by any time by the AT plus T off simply disables everything. So now to move a little more practical, I will open my terminal to show you first the interface on the simple AT commands. So I have one of those nodes connected. If I had a fresh board from the blister, I would need to first load it with the AT slave. So as I said, it's in the Cube firmware WL projects, Nucleo applications in Lorawan stack and Lorawan AT slave. I would open one of those projects, compile it, and load it into the microcontroller. For this session, I have prepared the hex file, so I can just copy paste it to the connected nodes, and it will program the microcontroller. Now, with the AT slave programmed, as you can see, if I send AT, it responds with OK. If I send AT question mark, I will see all the available commands that I can use. So now if I do AT plus tconf to configure the radio, this is a very long command that is not very human readable. So I will send a next command, which is the AT plus tconf equals question mark, and I will see the parameters in more readable way. So I set it to 868 megahertz with only minus dBm power because I have the two boards right next to each other, spreading factor 12, etc. Now I could use AT plus T-tone, but I will wait with this command because I want to show you a cross approach between the Cube monitor and the standard terminal. So I will start my Cube monitor now. Okay, it is loading. So if I had a fresh installation, I would need to import the flow. So I would use this menu, import, head to the AT slave folder. So I can quickly show you that is here, projects, Nucleo, applications, Lorawan AT slave. And here in the Cube monitor folder is the JSON file. Because I have everything loaded, I hit cancel. Otherwise, I would click import and everything would be loaded. Now, with the fresh installation, after loading the flow, I also need to set the serial ports, and that means opening these blocks by double click and editing and creating a COM port with the required parameters. So usually AT slave is on 960 and 8 data bits, no parity, etc. I will just use a dummy port right now because I don't want to block the other one, which is connected by terminal. When I have some changes, I need to hit deploy. And then I click dashboard to open the graphical interface. Now we are in the main menu for the RF functional tests. So if I open also my Termite, I have prepared the AT plus T-tone. So on this side, I start the RSSI test. I will see there's basically no signal, minus 20 dBm. No signal is detected. I send AT plus T-tone, and suddenly I see signal is received. If I do AT plus T off, I will stop the tests and you can see it rapidly dropped back to 120 dBm. Now I can also reverse the test. So this board will be transmitting. So I put the power -9 because I don't want to overload the RX. So now I am transmitting, and on this side I can do AT+T RSSI, and it will show me -25 dBm. So the carrier wave is detected. If I stop this and do the command again, I will see there's no signal, -23, 123 dBm. So now I close the termite and set back the COM port for the second board so that I can show you now the full features of the Cube monitor. I made changes, I click deploy, and then I go back to the dashboard. So we went through the RSSI test and continuous wave test that uses only one board, but then there is the packet error rate test, which uses both boards. So one of the boards is transmitting. So again, I set the lowest power. I can set other parameters. I will leave it as is for now, and I can start. And the other one will be receiving. And as you can see, we are receiving packets, and packet error rate is calculated. It goes on multiple frequencies. You can set it up the way you need it and see if there is some problem in the link. If I stop it and let's change the spreading factor to 7, for example, test will be much faster because the time on air is much shorter. Now for the last test, that is the TXRX, that is basically again the RSSI test plus tone test, but this time we use two boards. So for example, in your development, you can use the STM32WL Nucleo as a base board, and the other board would be your PCB, which you want to test if it's behaving as it's designed. So again, I start the test, and I can see I'm receiving the signal. I can stop it. It will go down. I can also show you, hopefully, my boards. And I can head back here, and we can play a bit more so that you can trust me that I'm not simulating anything. But as you can see now, there is -25 dBm. If I cover the antenna with my hand, it will slightly decrease. Or if I put the hand like this, it will decrease a slight. So it's no simulation, it's real hardware that is running right now on 2 Nucleo boards. I stop these tests, and we can move more to the Cube monitor tests. We are in the RF Test Explorer, and there's a hidden tab where is more tests to configure. We can do the very same tests for the FSK modulation, so not only LoRa modulation, but also FSK modulation can be tested. So again, there is the RSSI tests, continuous wave test, packet error rate test, etc. And then there is the LoRa airtime, which is a theoretical part. If you want to know how much time on air your packet will take, you enter your parameters, spreading factor, bandwidth, how long the payload is, how long is the preamble, if the length is explicit or not, if CRC should be calculated or not, and it will calculate you the time on air and duty cycle after what time you can transmit again. So if we change as before, the spreading factor to 7. Instead of 2.5 seconds, we have now 102 milliseconds. So it's more beneficial to transmit with lower spreading factor, but at the same time, it will rapidly decrease the range. So you need to find the threshold suitable for your design. Usually in Lorawan, we have the auto data rate detection. So it is changing based on the RSSI. The last part of the cube monitor is also command. It's basically a simulation of terminal. But the benefit of this is that any of the tests I have done using the graphical interface, I can now just click here and copy paste the command for my reference, or if I want to execute it from the simple terminal or any other application that would run some automated tests. I would lastly also mention that since the cube monitor is based on the Node-RED, I can also access it via internet. So if I enter my PC's IP address and a 1880 port, I will see the same interface as in the cube monitor. I don't need to use only this PC. I can use, for example, my mobile phone and access it via the same network. There is the flow. I can click also the dashboard and it will appear in a Chrome tab. So that should be all from my side. There are some important links to download the cube monitor, etc. I thank you for joining me on this presentation, and I hope to see you somewhere someday